Okay, honors geometry. Please make sure you are on day 2 right now. If at any time you need to stop the video to redo your notes or to catch up, please do so and just replay it. You can always stop and play it again. Homework, make sure this homework is done. You've checked your answers up on Classroom, and I will go over any of your questions tomorrow in class. All right away today, have your compass and straight edge ready to go. Before we start today's notes, I just want to do a quick review for you. If you want to jot this down, you can. If not, just make sure we know the answers to these questions here. So yesterday, in a triangle, we noticed a concurrent line in a triangle. All right, we noticed that the perpendicular bisectors were concurrent, which led us to a new vocabulary term, which was the point of concurrency for those concurrent lines. All three perpendicular bisectors intersected at the circumcenter. And then finally, we should know a special property about the circumcenter. All right, our special property, it is equidistant from the vertices. So that is what we should have gotten out of yesterday's class. Okay, we have a set of concurrent lines, which are called the perpendicular bisectors. They all intersect at the circumcenter, and that circumcenter is equidistant from the vertices. Today, I got another one coming at you. All right, this is why I mentioned yesterday it's so important we keep up with this vocabulary, whether it be index cards, quizzing each other every day, whatever's going to get the job done, because remember, you got a quiz coming up on Tuesday. All right, so let's go back to the day 2 notes. And what I want to start off doing, grab your compass and your straight edge right now. I want to do angle bisectors of a triangle. Specifically, I want to do an angle bisector for angle A and an angle bisector for angle B. So let's review this. And again, this is where you may want to pause the video, do your arc mark, come back, play it, just to make sure you guys keep up and don't fall behind. So to do an angle bisector, I put my compass point on A, and I make an arc through angle A. Then I come down to each point of intersection I made, each point of intersection, and I make 2 more arc marks below. 1, 2. So that's what my final construction should be. 3 arc marks. I grab my straight edge and I draw in my angle bisector through angle A. Done. Okay, now let's do the same exact thing for angle B. Put my compass point on B. Stop the film if you have to. Stop the video. Make an arc through angle B. Now I go to both points of intersection. Put my compass on each point. Make some more arc marks. And again, now from here, if you're going to start running into some former arc marks, these next 2 arcs do not need to be the same as the first. So if you wanted to make your compass open it up a little wider so you know where these 2 arcs will be, that's fine, just as long as these next 2 arcs are the same opening, but they don't need to be the same opening as your first one. So arc mark, same opening of your compass, go to the other point of intersection, and another arc mark. Line up your straight edge. Same deal. Draw in your angle bisector. Okay, now, if I had you do it for point C, we're not going to do it for point C, 1 for time's sake, and 2, you can see my diagram's already getting pretty crowded with all these arc marks. If we did the angle bisector for C, you would be absolutely correct in your thinking that angle bisector for C would intersect the other 2 at the same point. So what can we say about the angle bisectors of a triangle? The angle bisectors in a triangle are the vocabulary term we've been using, if they all intersect at the same point, are concurrent. So now we have another set of lines that are all concurrent. So if I go back to my chart I just started today with you, yesterday we found out the perpendicular bisectors in a triangle are concurrent. Today, oh geez, the angle bisectors are also concurrent. Okay, the angle bisectors are concurrent. So now you know two different types of lines in a triangle that are concurrent. Perpendicular bisectors and now angle bisectors. So going back to your notes, yeah, we had the circumcenter for perpendicular bisectors. For the angle bisectors, ready? That point of concurrency is known as the incenter. The incenter. All right, that is known as the incenter, that point of concurrency. So if I go back to my chart, hey, now I got another point of concurrency called the incenter. And yes, just like its circumcenter counterpart, it also has a special property. Okay, it has a special property. That special property is right here in the theorem. That the incenter, the bisectors are concurrent at a point equidistant, ready? From the sides of the triangle. Yesterday, it was equidistant. If I go back to my chart, it was equidistant from the vertices. The incenter is equidistant from the sides of the triangle. Okay, from the sides. So going back to our notes here, take a look. If I tell you point D is the incenter. Okay, point D is the incenter. There's a couple things you guys should be able to tell me here. First thing you should be able to tell me is that AD, DC, and BD are all angle bisectors. Okay, they are all angle bisectors. The reason I know that is, D's an incenter. Incenters are only formed by angle bisectors. So that's how I know all three of those lines that intersect at D are angle bisectors. From here, now I can use that special property, which is the incenter is equidistant from the sides. So take a look at my diagram. D to E, D to F, D to G, all congruent to each other. Okay, all congruent to each other by saying the incenter is equidistant from the vertices. Okay, so this is what I should get out of if I know a point is the incenter. Where are the angle bisectors and what lengths are congruent to each other? And if they're angle bisectors, remember, that tells you those two are equal. Those two and these two. That's what a bisector does, angle bisector. All right, so there's the incenter deal. Okay, next up, that was the same slide, so let's go to the next one. New vocabulary term, altitude. Okay, altitude of a triangle. Let's read through the definition here. Altitude, perpendicular segment from a vertex to the line contained in the opposite side. So an altitude is a segment, starts at a vertex, perpendicular to the opposite side. Starts at a vertex and is perpendicular to the opposite side. So once I hear this word perpendicular, what conclusion can I make on this diagram? Angle ADB and angle ADC are right angles. Altitudes form right angles, if you want to jot that little fact down. Altitudes form right angles. Okay? Altitudes form right angles. All right, because again, an altitude starts at a vertex, is perpendicular to the opposite side. So let's try out a constructing an altitude. Grab your compass straight edge. If you need to pause the video to catch up, please do so. First of all, anybody know what type of triangle I'm working with here with ABC? Because angle B looks like a little bit more than a right angle, doesn't it? Looks like an angle bigger than a right angle or an angle bigger than 90. So this would be what type? Obtuse. Okay, and I picked an obtuse triangle on purpose. All right, because I want to construct an altitude from point A. From point A. So you know it's got to start at point A and be perpendicular to the opposite side. Well, hold on a second. We're going to use our compass in a second. So let me just do my drawings on here. That's not going to be the altitude. There's no way that's perpendicular, right? Nope, no way that's perpendicular. Where is this altitude going to be so that it starts from A and is perpendicular to my opposite side? Grab your compass and straight edge now. We have done this construction before, which is from a point, in this case A, I need to draw a line perpendicular from A to BC. And if you remember, the first part is you're going to do that little smile arc where you need it to intersect the opposite side in 2 spots. But watch, guys, watch my compass. 1, there's no way I'm going to be able to intersect BC in 2 spots. Think you got any suggestions? Hopefully some of you are thinking or saying under your breath, extend the line BC. Yep, you're correct. So let's extend BC a little bit. So let's extend BC. And here we go. Now I can make it intersect twice, right? 1, 2. I like to open up my compass a little wider for the next 2 arcs. Go to each point of intersection. And I'm going to make 2 more arcs that intersect each other. We're good. Okay, now line up your straight edge. Yeah, this altitude for an obtuse triangle, one of the altitudes will be located outside the triangle. Draw it down. You can stop here if you want. You can continue it through, whatever floats your boat. All right, I'm going to stop it right at my line, and there's your altitude. And let's make it an altitude by putting a right angle there. Okay, so for an obtuse triangle, one of the altitudes is located outside the triangle. All right, one of the altitudes. Now, let's just say, and we're not going to for time's sake again, I did the altitude from C and I did the altitude from B. They would all intersect each other. All right, all 3 altitudes of a triangle are concurrent. Okay, all 3 altitudes of a triangle are concurrent. So if I go back to my chart, I'm throwing 3 at you today, or 2 at you for 3 total. Another pair of lines that are concurrent, altitudes. Altitudes are concurrent in a triangle. What's their special name where they all intersect? Their point of concurrency, if we go to the next page, is called the orthocenter. All right, that is the point of concurrency for the altitudes. Okay, the point of concurrency for the altitudes of a triangle. All 3 altitudes intersect at what's called the orthocenter. And unfortunately, this might be good news for some of you because I've been throwing a lot of vocab at you, but there is no special property. No special property of an orthocenter. None. Okay, it's not equidistant from anything. There's no special property about it. But I would like you to know where it's located depending on what type of triangle I have. All right, depending on the type of triangle, where is the orthocenter located? Well, let's go through. Let me start with the one we just did, which is an obtuse triangle. Okay, if I have an obtuse triangle, where would the orthocenter be located? Well, let's take a look back, right? We just learned that one of the altitudes would be located on the outside. So no matter where the other 2 altitudes are, the orthocenter should be on the outside of the triangle because the one altitude is, right? So somehow, if I keep drawing it in, my altitudes here, they're going to have to somewhere intersect on the outside. Okay, they'll have to intersect somewhere on the outside of the circle. So if you have an obtuse triangle, the orthocenter will be on the outside because one of the altitudes is on the outside. Right triangle. Okay, if I have a right triangle, which I have up here. I don't know if you guys see this or not, but in a right triangle, two of the altitudes are already two of the sides. Take a look. Altitude, altitude. Right? Look, listen, remember go back to the definition of an altitude. Starts at a vertex, perpendicular to the opposite side. Starts at a vertex, perpendicular to the opposite side. Those are altitudes, also known as the legs. And where do they meet? Or at least those two meet, and the third one will as well. There it is. There's your orthocenter on a right triangle. It's the intersection of the legs. Okay, intersection of the legs. In a right triangle, 2 out of the 3 altitudes are the 2 legs. And then finally, the only other type we have to worry about is an acute triangle. Okay, in an acute triangle, all the altitudes are located inside. None are located outside. That's only an obtuse triangle. So anytime I have an acute triangle, the orthocenter will be located somewhere inside. Okay, inside. So recapping what we should get out of this discussion today. And look, guys, I get it. It's not the greatest. It's on film. It's not me actually up on front helping you guys out. All right, we'll clean anything we need up tomorrow. But here's what I need you guys to get out of today's session. Angle bisectors all meet at the same point in a triangle. I don't care what type of triangle it is. All 3 angle bisectors will always meet at a point called the incenter. That point will always be equidistant from the sides. Not the vertices, that's the circumcenter. But the incenter will always be equal distant away from all 3 sides. And then we introduce what's called an altitude of a triangle. What's an altitude? Starts at a vertex and will be perpendicular, that's awful, I know, perpendicular to the opposite side. All 3 of them, because there's only 3 altitudes in a triangle, and if you have all 3, they'll intersect at the same point, which is called the orthocenter. Orthocenter. All 3 altitudes intersect at the orthocenter, and good news for us for today, there's no special property. So that's what, and be able to construct an altitude as well now. Okay, I give you a triangle, you'll be able to swing the smile face, 2 more arcs below it, and draw in your altitude. All right, and then tomorrow we got 1 more. All right, we have 4 pairs of concurrent lines in a triangle, 4 sets. All right, so let's make sure we have these down pat. I'll answer all your homework questions from Tuesday night and tonight, and we'll get it all cleaned up and move on. Okay, you guys can go ahead and start your homework. Thanks, guys.